Today, we're going to explore reflections and how we can create objects that bounce when it hits a wall. Of course, it's gaining a little bit more speed than it should, but we'll talk about that. First thing you need to know is the math behind it, and I promise this is not scary at all. So basically what you're looking at here is what happens when the puck hits the wall. Well, it bounces off and it forms this sort of triangular shape. So what we're calculating is position A to position B. How do we get to position C? Well, the answer is very straightforward. A stays the same, A equals C. B is multiplied by 2 and you subtract the original value to get C. So when you look at Z, you go to hit Z2, you multiply this by 2 to get 6, and you subtract 0 and you're at 6. And this continues on. So if you take 6 and multiply it by 2, you get 12, subtract 3, now you've got 9, and it remains at position B's -10. And that will continue as long as you're in the horizontal bouncing direction. But when you get to the vertical bouncing direction, it's the inverse. And in this case, you'll see that Z stays the same, but X is the one that's been doubled. This is interesting because now you know you need to flip your math around. When we use the reflect code block, we need to input a normal. And what a normal is it's defining which side of an object we're bouncing off of. So a normal is a face of a cube. The upper face is 0, 1, 0, the lower face is 0, -1, 0, and these side faces are a number of 1, 0, 0, 0, 0, 1, and so on. And they're just vector values. Now, I'm not 100% on normals. I've just scratched the surface myself. I'm still learning just like everyone else. And if you have any information to share, please leave it in the comments below. Thank you. When you think of the puck coming in and it bounces off of this side, in our minds, that's pretty obvious. But what if that same point where it was coming in at happens to now be here, not here? So if we bounce off of this side, it bounces this way. But if we hit that point here, it bounces this way. And so it's important to know which face, and in this case, which normal we're bouncing off of. This allows you to calculate the normal. And I'm not gonna lie, I don't fully understand it, but what I do understand is you take this value and this value and you multiply them together to get the area, and the area is equal to the normal, where this line represents the normal's distance. And then you need to use a normalize to bring it back into a normal value. We didn't have to use it in this case because I kept everything lined up with the grid, so everything was in 0, 1, 0 form. But if you were going to have something rotated, this math will become important and you're going to have to calculate your normal before you can input it. When this puck enters one of the wall triggers, each of these walls has a trigger on it which defines when the puck has hit the wall. And when it does hit the wall, we get this trigger enter with object event. When the puck enters the trigger, we need to know what the current normal is. So we're using this OR statement. If the X value is greater than, or if the X value is less than certain points, meaning it's on certain sides of the grid, then we know to set the normal to 0, 0, -1. And if we have the opposite going on, we have the Z position, and we're also setting that to 1, 0, 0. The next thing that you need to note is that you have to save the previous position and you need to get the current position. So after everything's done, we save the current position as the previous position, and we set the current position to be the current position of self. We then get the direction between those two by normalizing pre-position minus current position, and then we can add to the velocity by using the reflect. And so what reflect looks like without anything in it is you have a vector and a normal. Now these are both technically vectors, but the normal is the 1, 0, 0 or the 0, 0, 1, and the vector is the amount that we're going. And so we take direction. So remember, we just calculated the direction, but we normalized it down to a 1 meter length. We multiply it by 2 because we need to get it going. We want to give it some speed to get it across and moving, so we've multiplied it by 2. What reflect does is it takes that vector value, then it reflects it across that normal. And remember, a vector can also be viewed as a length. And when we normalize it, we've normalized it to a 1 meter length, which is a direction, and then we've got the direction going in the next direction. And by multiplying it by 2, we have a length of 2x, which can be converted to velocity because we can now move it in that direction with a speed of 2x times what 1 would be. And while this works remarkably well, there is a better method. And so I was talking with Spastic about how to get this to work better because the bounces weren't entirely accurate. And what we ended up doing is we made a grid similar to this one with 4 triggers, But when trigger was entered, we sent this event with a delay, and rather than adding to velocity with reflect, we added to velocity with its current velocity. So we just said, let's amplify the velocity, because the biggest problem and the reason we needed to use reflect is because super ice, when it hits a wall, comes to a near dead stop, but not exactly. It has enough motion that we can continue that motion and use the built-in physics engine in the horizon to get the direction, which works, I'm not gonna lie, much better. Reflections can be very useful depending on what you're using them for, but if you want to build an air hockey table, I highly recommend putting in a delay and then just amplifying the current velocity. All right, you guys, thank you so much for checking out this video. If you have any other questions about math topics or anything else, I'd be more than happy to cover them, and we will see you in the next one. Bye!